Okay, before we look at our next example, let me mention a couple of things here. So you'll notice that I've put back on the screen the definition of a partition of a set capital X and the theorem that we just stated about any equivalence relation generating a partition. And so notice that underneath the definition I've added a new sentence that I've designated by an asterisk or star, and that sentence is just an alternative way to state conditions 1 and 2 in a single sentence together. That if we have a partition, then it's got to be the case that every element of the underlying set X is in one and only one element of the partition. And remember, elements of the partition are subsets of capital X. And also here, notice that the theorem, again, says that if we have an equivalence relation, then it will be the case that the set of the equivalence classes, according to that equivalence relation, will be a partition of the underlying set. So you'll recall that we saw a whole bunch of equivalence relations in the preceding 2 lectures. And so this theorem tells us that for every one of those equivalence relations, if you take the set of its equivalence classes, that will be a partition of the underlying set X that the relation is defined on. And so that's going to be helpful. In fact, we'll come back to that after we look at this next example. So for this next example, let's use as our underlying set X the set of 52 cards in a standard deck of cards. So this set is going to consist of the ace of spades, 2 of spades, 3 of spades, out to the queen and king of spades, and then the 13 heart cards, 13 diamond cards, and the 13 club cards, culminating in the jack, the queen, and the king of clubs. 52 cards. Each card is an element of capital X. And so let's look at several possible, potential, or partitions, candidates to be a partition of the set capital X. And let's start with the set consisting of just one element, namely the set X itself. And of course, we just saw that a few moments ago, and we saw that that's always the case, that that's going to be a partition. But let's just point that out again. This is a set with a single element. The element is a subset of X, a non-empty subset of X. And so this is a partition. It's the smallest partition in the sense it's the only partition that has only one single element in it. So let's look now at several other potential partitions of the set capital X. So let's first look at the set we'll call P, and that is the set consisting of the 52 singleton subsets, singleton sets for the underlying set capital X. So it's a set consisting of the singleton set with the ace of spades in it, the singleton set consisting of just the 2 of spades, and so on. So it's all the singleton sets. And so, again, as we saw a few moments ago, the set of all singleton subsets of a set of the underlying set capital X, that's always going to be a partition. And, of course, we can verify that according to the this star condition that defines a partition, so long as we're talking about non-empty subsets of the underlying set. Let's define another potential partition, and this is, we'll call this script P prime, and that consists of the four elements. Each element is a subset, a non-empty subset of capital X. It's the spades, the hearts, the diamonds, and the clubs. The 13 spade cards are S. The 13 heart cards, it's capital H. the 13 diamond cards as capital D, and the 13 club cards as capital C. Is that a partition of capital X, the set of all cards? Yes, it is. Each of the elements of the partition, each of the 4 elements of the partition, is a non-empty subset of capital X, and every card, every element of capital X is in one and only one of these suit sets. It's either a spade, a heart, a diamond, or a club, and not 2 different sets. And so that's a partition. Let's look at another potential partition. Let's say script P double prime, which will be the set consisting of just 2 elements, R, the set of red cards, and B, the set of black cards. Is that a partition? Yes, same thing. We've got, in this case, only 2 elements. Each of them is a non-empty subset of capital X, and every card is either a red card or a black card, and not both. So we've got another partition. Let's take another set. We'll call it script P triple prime. That is a set. It's a set with only 2 elements, capital F and capital N. Capital F, let's say, is the set of face cards, and capital N is the set of number cards. So capital F has 12 elements, the 12 face cards. Capital N has 40 elements, the 40 number cards. Again, that's a partition because both of the elements of P triple prime are non-empty subsets of capital X, and every card is either a face card or a number card, and not both. Another example, let's call this set P hat, script P hat, and that consists of the red cards, the black cards, the face cards, and the number cards. 4 elements. And is that a partition? Well, every one of the elements of P hat is a non-empty subset of capital X. Every card, every element of capital X is in one of the elements of script P hat, but is not in one and only one element of P hat. Every card is actually in 2 of the elements of P hat. Every card is either red or black, so it's in one of those 2 sets, and it's either a face card or a number card in one of those 2 sets. So that is not a partition of capital X. Let's take that one off the screen then, and let's look at one last potential partition, and that's going to be a set we'll call script P tilde, and that is a set with 13 elements. And the elements are, first, the set capital A, which is the set of 4 aces, the set 2, which just give it the name 2, and that's the set of 4 deuces, 2s, all the way out to the set capital J, which is the set of 4 jacks, the set capital Q, which is the set of 4 queens, and the set capital K, the set of 4 kings. So that has 13 elements, P tilde, and again, that's a partition, because all the elements of P tilde are non-empty subsets of capital X, and every card is in one and only one of the elements of P tilde. Now, there's several things to notice about this somewhat extended example here. First, of course, we could have made up lots of other partitions as well, and we'll maybe mention 1 or 2 of the possible partitions in a few moments. But let's just work with these. The first thing to notice, I think, is that our theorem here says that whenever we have an equivalence relation, it will generate a partition, the set of equivalence classes. And that's how all the partitions we've seen so far, that we had equivalence relations that generated the partitions. Here, that's not the case. None of these partitions were defined by an equivalence relation. We didn't define an equivalence relation on capital X and then use that and take the equivalence classes and make up the partition. So these partitions did not come from an equivalence relation. So this theorem doesn't really tell us anything about this example. But on the other hand, notice that we could define an equivalence relation from one of the partitions. So, for example, let's take P, script P prime. That's the partition that consists of the spades, the hearts, the diamonds, and the clubs. And suppose we define an equivalence relation by saying X is equivalent to Y in the underlying set, capital X. If we take two elements of capital X, X and Y, we'll say they are indifferent to one another if there exists some element of P prime such that X and Y are both in that same element. So I've used capital E for the name of a generic element of the partition, and I've actually used capital E for a reason, because we often use capital E as the notation for one of these elements, because we're often talking about events in probability or statistics, and I'll come back and say a little more about that later. So I'm going to use capital E for generic elements of partitions here, and so here we're defining an equivalence relation on the underlying set capital X by saying two elements are equivalent if they're in the same element of the partition P prime. And so that you can easily check is an equivalence relation. That's going to be reflexive, symmetric, and transitive. I won't go through the details. You can check that. Simple, trivial to do. That is reflexive, symmetric, and transitive. For example, for script P prime, the partition consisting of spades, hearts, diamonds, and clubs. But that's true for each of these partitions. When I look at P double prime, the partition consisting of red cards and black cards, again, we could define an equivalence relation on the underlying set capital X by saying two cards, two elements are equivalent if they are in the same, I would say equivalence class, but we don't start with equivalence, we start with the partition. So these two elements are equivalent if they are in the same element of P. This should now be P double prime, if they're in the same element of the partition, the same subset of capital X. Same thing for P triple prime. We would say that we could define an equivalence relation between the cards by saying that two cards are equivalent if they're either both face cards, so they're both in capital F, or they're both number cards. They're both in capital N. And they're not equivalent if one's in F and one's in N. That's an equivalence relation, as you can check, that it's reflexive, symmetric, and transitive. So, in fact, that is true in general. That's always true if we have a partition and we define an equivalence relation by saying that two elements of the underlying set are equivalent if they're in the same element of the partition. That's always an equivalence relation. So it's a kind of converse of the A part of our theorem, so that's the B part of the theorem that I promised a little earlier. And that says that if we have a partition, it's always the case that the relation, the binary relation defined in this way, will always be an equivalence relation. So you can see then from this theorem that it's really saying that equivalence relations and partitions are kind of, in a certain sense, the same thing, just expressed in different ways, in different terms. Equivalence relation is a binary relation of a certain kind. A partition is a collection of subsets of our underlying set, a certain kind of collection. And this theorem tells us that when we have one, we have the other. If we have an equivalence relation, as in part A, then we've got a partition, the set of equivalence classes. Conversely, if we have a partition, as it says in part B, if we have a partition of the underlying set, then that always defines an equivalence relation, because it's always the case that we can say all of the elements that are in the same element of the partition, the same partition part, the same block in the partition, if you like, those are equivalent to one another. That's always an equivalence relation. That's a fundamental idea that runs throughout mathematics and really throughout economics as well. And as I've said before, you're going to see that over and over again. And you can see Lloyd Price singing about it. You'll see that over and over. And in fact, we will see this when we apply these ideas to modeling information in economics and game theory in a subsequent lecture. Now, another thing to notice about this example is that some of the partitions here seem like they are finer than other partitions. For example, let's take the partition P consisting of the 52 singleton subsets of capital X. Now, that partition seems like it's a lot finer somehow than, say, the partition P prime, consisting of just the four sets S, H, D, and C, the spades, the hearts, the diamonds, and the clubs. And then that partition, in turn, seems obviously finer than the partition consisting of just the one set, capital X, which seems like the coarsest possible partition we could have. And in fact, P seems like the finest partition we could possibly have. Now, this idea seems like it might be kind of important, and in fact it is quite important. This idea is kind of central to modeling information as we're going to do in a subsequent lecture. And so, because it's important, we can't just settle for having the concept be kind of this informal statement of, well, the partition P seems like it is finer than P prime, and so on. We need something that formalizes this idea and captures more precisely what it is we actually mean by one partition being a refinement of another or being finer than another. So in order to do that, let's first look at the partitions P prime and P double prime. So for P prime, we have four elements, each a subset of capital X, and notice that the set of spades is a subset of the set of black cards. The set of hearts is a subset of the set of red cards. Diamonds, subset of the red cards. Clubs, a subset of the black cards. And so every one of the four elements of P prime, every one of those four sets, subsets of X, S, H, D, and C, is a subset of one of the elements of P double prime, and it does seem like P prime is a kind of refinement of P double prime. We've refined the set consisting of black cards and red cards, the partition consisting of black cards and red cards. We've refined that into a finer partition where the black cards have been refined down to spades on the one hand, clubs on the other, and the red cards have been refined down to hearts on the one hand and diamonds on the other hand. And so that idea that each of the elements of the P prime partition has an element of the P double prime partition that it's a subset of, that we can write down. So that says for every element of the P prime partition, there exists an element of the P double prime partition, and they're not going to be the same elements, so I need to distinguish this E from this E. Let's put a prime on that one. There exists an element of the P double prime partition for which this is a subset of this. And so this captures exactly what we set up here in this line up here. Notice that every one of these four subset relations is captured down here. That is, one of the S, the H, the D, and the C, each one of those is a subset of P prime, is an element of P prime, and then we have two elements of P double prime, B and R, and in each case, an element of P prime is a subset, that's supposed to be subset, not less than or equal, is a subset of an element of P double prime. And so let's do one more. Let's look at P and P prime, which we already mentioned informally. And so I want this to be P now, and I want this to be P prime. So let's take those off of there. Okay. And so now notice that it is the case that for every one of the 52 elements of P, there is one of the four elements of P prime that the P element, the singleton set, is a subset of one of the four elements of P prime. So let's give that a name. So when we give these a name like this, these conditions, and we say they're really important and that they're kind of general, as it seems like is happening here, what do we almost always do? Yes, indeed. We're going to elevate this to a definition. So here we have our definition. It says that a partition P is as fine as another partition P prime, or we would say it's a refinement of P prime. And we would also say that P prime is as coarse as P, or is a coarsening of P, exactly when this condition is satisfied. Exactly when, for every element of the finer partition, there is some element of the coarser partition such that the finer partition's element is a subset of the coarser partition's element. And you'll notice that, first of all, this is a binary relation among partitions. That is, it's a binary relation on the set of all partitions of some underlying set X, like we have here. And you'll notice that the notation I've used for this binary relation is the less than or equal symbol, not the symbol that we've used for the binary relation that's a pre-order, for example, preference and indifference. And this is pretty much reserved for relations that are antisymmetric, order relations that are antisymmetric. That is, relations that are transitive, reflexive, and antisymmetric. And indeed, you see here, this remark says that indeed this relation that we've just defined is a partial order. It is transitive, reflexive, and antisymmetric. And you'll recall that antisymmetric, at least in this context, means that if P is less than or equal to P prime and P prime is less than or equal to P, and in this context, less than or equal means a refinement of. So if P is a refinement of P prime and P prime is a refinement of P, then antisymmetry says they have to be the same partition. And indeed, that's the case. This remark says that indeed this relation is antisymmetric, and so it makes sense to use this less than or equal symbol here, because if we have less than or equal going both ways, we get equal. So let's go back over here and let's make a note of the refinement relations that we've already established. We've already shown both of these refinement relations, that P is a refinement of P prime and P prime is a refinement of P double prime. You'll notice that I've used strict inequalities here, and that's because P is a refinement of P prime, but they're not equal. So we use a strict inequality just like we do with numbers. And we would say P is a strict refinement of P prime, and P prime is a strict refinement of P double prime. And of course, the refinement relation is transitive, and of course, the strict refinement relation can be easily shown to be transitive as well. So this would imply then that therefore P is a strict refinement of P double prime, which of course it is. I mean, we can see that directly. But here I just wanted to point out that the transitivity actually is useful in this particular case. We didn't really need it. And here I want to focus for just a minute or two on this relation right here that we showed earlier. And of course that came from these four subset relations here, that the spades are a subset of the black cards and so on for the hearts, the diamonds, and the clubs. And so let me write that a little differently. Here I'm going to point out that the spades and the clubs, the set consisting of the spade set and the club set, that set is, of course, a partition of the set of black cards. And so we don't really have a notation for this saying one thing is a partition of another, but let me actually make up a kind of ad hoc notation just for our purposes right here. I'm going to put a pi in here and say that pi means this set of subsets of capital X is a partition of this set here. And of course, these are subsets of B. S is a subset of B, C is a subset of B, so it's easy to see, or easy to establish, that this set of these two subsets of B is a partition of B. It's pretty clear. And also, of course, the same way, the set of the hearts and the diamonds, the set consisting of those two subsets of R is a partition of R. And so that's another way of actually seeing that the partition P prime is a refinement of the partition P double prime, because for each of the elements of P double prime, the set of red cards and black cards, for each of those two sets, each of the two elements of P double prime, the red cards and the black cards, there are elements of P prime, the spades, hearts, diamonds, and clubs. There are elements of that that form a partition of the set B and a partition of the set R. So this actually is a good alternative way of writing the definition of a partition. And so let me do that here. You'll see here, this is a little close here, so let me actually erase these two things here, so it sort of sets off this remark a little better. So here we have another remark that says that P is a refinement of P prime if for every element of P prime, every element, say E prime, a subset of our underlying set, if every element of P prime, such as E prime, there are elements of the finer partition P that form a partition of E prime. And that's what's really going on over here. So you can see that here the set B has a pair of elements. I'm trying to see the best way to say this here. The set B, for the set B, there are two elements of the set P prime that together form a partition of B. And for the set R in P double prime, an element of P double prime, there are two elements of P prime that form a partition of R. So this is just repeating what we said earlier, but trying to do it in a way that we can see it fits with this remark, this alternative definition of a refinement. And so, oh, by the way, notice that these are remarks, so they're things that have to be proved. They're remarks because they're really easy to prove, but they do require proof. They're both straightforward to prove. The first remark, that the less than or equal, the refinement relation, is a partial order, reflexive, symmetric, reflexive, transitive, and antisymmetric. And the second one, this alternative condition, alternative definition of refinement. I should add, I've never actually seen this alternative definition anywhere else, but I think it's actually a very useful way to think of refinement of a partition. It kind of captures the idea of refining, because we take the partition P double prime, for example, here, and we take each element of P double prime and we further partition it. So let me take another example here. Let's make up the set consisting of the jacks, the jack set, the queen set, the king set, and the number card set. So this is a refinement of, this is a strict refinement of the set consisting of face cards and number cards, which of course is just P triple prime here. And so this is a strict refinement here, but notice that J, Q, and K is a partition, with our new ad hoc notation pi here, is a partition of the set F of face cards, and N, the trivial partition of N, that is a partition of the set N. So here we have the set N, and we have what we call the trivial partition of N, the set consisting of the set N. And so notice that this is actually now I'm going to do something a little tricky here. This is actually, I'm going to take this off and write the trivial partition of F. This is a strict refinement of the trivial partition of F. And let's get this off. This is a partition of the trivial partition of N. And of course, this is less than or equal because it's not strict refinement of this, but the partition consisting of just N, the trivial partition of N, is a partition here. And now I want to finish off with a counterexample. Let's note that P is not a refinement of P double prime, of P triple prime, sorry, and P triple prime is not a refinement of P prime. So this is a counterexample to a couple of things. One, it's a counterexample that shows that it isn't just the case that having more elements makes one partition a refinement of another. P prime has 4 elements, spades, hearts, diamonds, and clubs. P triple prime has only the 2 elements, face cards, number cards, but it's still not the case that P prime is a refinement of P triple prime. It's also a counterexample showing that the refinement relation is not a total order. It's not a complete binary relation. So I think that kind of wraps it up. I think we're now pretty well versed in partitions and equivalence relations and the relationship between the two. And I think that puts us in a pretty good place to now learn about preferences and utility functions and the relationship between the two, and to learn about modeling information in economics and game theory. So that wraps it up for today. See you all next time.